In this video we will discuss chapter 4, matrix decompositions, and we will start with the notion of the determinant. Determinant of n times n matrix is a function from matrices to real numbers. Determinant can be denoted by this det sign, or by these vertical bars. For n is equal to 2, determinant has the formula, so you can see it here. Determinant of this 2 by 2 matrix is the product of the main diagonal elements and subtract the product of the sub-diagonal elements. For 3 by 3 matrix, the determinant can be calculated by Sarro's rule, or sometimes it's called triangle rule. So you can see it here. This is 3 by 3 matrix given, and the determinant is, first of all, we take the product of these three terms on the main diagonal, A11, A22, and A33. Then we add the product of terms on this triangle which cross this main diagonal. So this is A21, A32, and A13, and we add the product of another triangle, A12, A31, and A23. And then we subtract the, first of all, product of the sub-diagonal elements and the product of corresponding two triangles. Okay, and for general case, the determinant can be calculated using Laplace expansion, which can be expansion along column or expansion along row. So here you can see the two formulas for the formula for the determinant in each case. So here we can see that we have the sum over k. So if it's column, so we go through the column. And this is minus 1 to the k plus j. So this is the sign of the summand in each case. And the sign determines by the sum of row and column of the corresponding element. Then we multiply by the value of this element, and then by determinant of a submatrix AKJ, which is called cofactor. And similarly, we have expansion along row. And let's see on an example how this can be done. So let's consider this example of 3 by 3 matrix. And we will use Laplace expansion along the first row. So what do we have? The determinant of A will be equal to, so firstly we take the first element of the first row, which is 1. Then multiply by determinant of the cofactor. And the cofactor appears here if we cross the first column and the first row of the determinant. So it's 1, 2, 0, 1. Then we subtract. The next sign will be minus, because the next element has second column and first row. If we add, you get 3, and minus 1 to the 3, we get minus sign. And we take the element, the next element, which is 2, okay, and multiply by cofactor. Again, what we do, we cross the second column and the first row, we get 3, 2, 0, and 1. Then we add 3 times corresponding cofactor, which is 3, 1, 0, 0. And next we will use the formula for 2 by 2 determinant. So here for the first one we have 1 minus 0, we have 1. Then we subtract 3 minus 0, we have 3, and times 2 we have 6. And we add, this is just 0. So the result is minus 5. So this is the example of cofactor expansion along the first row. Of course, we can choose any row and any column which is convenient for us. In this particular case, of course, it's easier if we choose, let's say, the third row. In this case, we have here 2 zeros, so we have only one summand, 1 times, and the cofactor of, so this is 1 times the cofactor of this three element is 1, 2, 3, 1. So we get 1 minus 6 again, which is minus 5. And so on. If you want, you can choose instead of row, you can choose column and make it with a column. Okay, next, let's consider the properties of the determinant, which are quite important. And the first one is that the determinant of product of two matrices can be calculated as the product of corresponding determinants. The second one is about invariant transposition. It means that if we take a transpose of the matrix, we do not change its determinant. Another about the invertible element, about the inverse element of matrix. So if we want to calculate the determinant of A inverse, we just take the determinant of A and 1 divided by the result. This formula comes easily from the first one. If here in the first formula, in this formula, instead of B, we will take A inverse. Here we will get just identity matrix. Determinant of identity matrix is 1. And on the right side, we have determinant of A times determinant of A inverse. From this, determinant of A inverse will be 1 over determinant of matrix A. And the next property is about similar matrices. Similar matrices, let me remind you what they are. So A and B are similar. If there is some invertible matrix S such that A is equal to S, B, S inverse. So A and B are similar if we can get A multiplying B by S and S inverse from both sides. And this is also the way, in fact, to convert between two bases. And therefore, we can say the determinant is invariant under choosing some basis for a space. So it doesn't matter in which basis you consider matrix. It always has the same determinant. And next property is about adding and multiplying columns and rows to another one. Doesn't change the determinant. This property also may be helpful in calculating the value of determinant of A. And then multiplication of columns and rows by some real number scale the original determinant by lambda. In particular, if we multiply the whole matrix by a number lambda, this lambda will come out to the power n. A is n times n matrix, so A has n rows. From each row or from each column we get its own lambda, and so we get lambda to the n. And if we swap two rows and columns, we will change the sign of determinant. Let's now look at the property of adding and a multiple of column and row. And let's use this property to calculate the determinant of a matrix. Let's consider the same example as we had before. But to start this, before I want to remind you the notion of upper triangular matrix and lower triangular matrix. So for example, upper triangular matrix is the matrix in the form when you have 0 below the main diagonal and some numbers above the main diagonal. And for this type of matrix, we have its own formula for determinant. This is simply the product of these elements on the main diagonal of the matrix. And let's compute the determinant using the following idea. we will firstly reduce the matrix to the upper triangle matrix, and then we will use that previous property to say that the determinant will not change. So let's see how we do this. The determinant of A will be equal to the determinant of, so let's leave the first row on its place. And for the second row, what we will do, multiply the first row by minus 3 and add to this. So we get 0, then we get minus 5, then we get minus 7. And the last row will again stay as it is. So you see that we get upper triangular matrix, and so the determinant of this will be just a product of 1 times minus 5 times 1, which is minus 5, again, as before. Okay, that's it for this part about determinant. Thanks for listening.